Okay, welcome to an introduction to robotics. So this is class AIT 139, and my name is Richard Hartman. Okay, so just even though there's no lab associated with this class, I just want to point out to you that the first thing we always need to keep in mind when we're talking about robots is to be careful and be safe. So always think safety first. And so if you see here, I got a link that you can follow, a little YouTube link. It's just a little bit of fun, but you can click on that and see about, what you shouldn't do, which is pretty obvious as you watch the video, and you've probably seen it before. But always want to think about safety. Okay. All right, and so we'll be anytime you're working with standard industrial robots, they're going to be in a work cell, which should be enclosed and have monitoring of some sort. So in the classroom, we have our LR mate robots that actually use a laser fence to indicate whether body parts or something has crossed into the area of the robot. And we'll cover that in chapter 4 on safety. All right, so just a little bit about me here. Again, my name's Richard Hartman. I'm full-time faculty here at Stark State, and my office is B215R for Richard. And so if you need to get a hold of me, probably the best way to get a hold of me is via email. So here's my email address, rhartman@starkstate.edu. Notice there are 2 N's on Hartman. And so you need to make sure you put that second N on there for the email to be received. But you can send me an email and just let me know if you're planning on coming to my office hours, or if you can't meet during my office hours, to meet at another time. All right. So I kind of got started at this out of high school. I joined the military and did fire direction control for the United States Army. So this is just some pictures of some of the equipment. As you can tell, it's older equipment, but we use these computers to calculate the type of fire, the direction, how much lift, various information in there. And I actually just repaired the computer equipment shown in here. And down at the bottom is shown a multiple launch rocket system, or MLRS. Okay. That was not me in the background there, by the way. So, all right. So after being in the Army for a while, I got out and went into college and studied engineering, specializing in automation and controls. So I did a set point calculator design for my master's at Goodyear. I also did some automation for the United States courts for several years, and I've been here at Stark State College for 20 years, and I am a certified Fanuc instructor for the standard and the vision courses that they offer. All right, so for today's objectives, we're going to look at some definitions. We're going to talk about some of the early robots, classifications of industrial robots, types of automation, and the role of robotics. Okay. All right, so the term robot actually came from a play by Karl Čapek, and he was Czechoslovakian, and the word robota means forced labor. So that's actually kind of the origin of the term robot. Okay. Now, early in the 50s, there were some various designs for robots. So the first patented robot was in 1954. It was called the Unimate. Okay, and it was actually purchased quite a few years later by General Motors and used in a die casting operation. Okay. So you can kind of see there, there's a term anthropomorphic, which means human-like. So when we look at a lot of the modern articulated robots, the idea is that, you know, we want to kind of try to mimic human motions, and so that's what this big long word means. Okay. All right. Japan first got started into the robots about 1969, and they formed the JAR Foundation. Okay. Another big foundation for robotics, which is actually probably the primary one, is the RIA. This is a robotics Institute Robotics organization. It's a worldwide organization and was founded in 1974. Okay. Fanuc, which we'll talk mainly about Fanuc robots because that's what we actually have in the classroom here at Stark State. And so even though they're a Japanese robot of Japanese company, but they have the largest market worldwide for robots, and so followed pretty closely by ABB, but Fanuc definitely has the largest market share worldwide and in the United States. And they first entered the market in 1981 in the U.S. Okay. All right, so let's look at the definition of a robot. Okay. So a robot is an automatically controlled, reprogrammable, multifunctional manipulator designed to move material, parts, tools, and specialized devices through various programmed motions for the performance of a variety of tasks. Okay, and so you'll find this definition on page 9 of your book, the Ross book, third edition of the Ross book. I have a link down here. You can click on that through the slides. And I just kind of ask, and the question here is, are these robots? And when you watch that, it's actually a video of something called the Robot Wars. You may have seen it before, but the thing that gets me, they call these robots, but in reality, these robots are being controlled by remote control. So they're really like modified remote control cars kind of deal. And so they technically don't meet the definition of a robot if we see up here the word automatically. So a robot is automatically controlled. So it's running by a program that was pre-programmed. It's not being run by joysticks on a remote control. Okay, so and there's some debate about that, but basically, and my feeling is for it to be a true robot, it needs to be running autonomously and doesn't have a human telling it when or where or which way to move every second. It's been pre-programmed, and then it performs the tasks based on that program. Okay. One other thing while we're on this slide that I just want to point out to you, and this will be true throughout the class, but as you're going through slides, anytime you see words that are highlighted in maybe a different color or bold font or anything like that, I would recommend that you make extra note of those, because a lot of times when you're going through the quizzes and the homeworks and things, questions, when you run into a question in the homework or something, it's probably related to a word or a phrase that's been highlighted within the slides. So just a hint as you're going through, these are kind of keywords that you're probably going to see. Now, not all the times. There might be some that didn't get highlighted, but most of the time you're going to find them that if they've been highlighted, there's a question somewhere in the homework or quiz or exam that's going to show up. All right, another term, and they didn't really get into this in the book that we have this semester, but it's called Computer Integrated Manufacturing, or CIM. And CIM has actually been around for a very long time and a lot of different ways, and it's just ever expanding. And so what we see now here is the computer integrated manufacturing is basically talking about the fact that we're using computers and collecting all the information about the manufacturing process. Everything from the raw materials, how many raw materials we're going to need, when they're going to be delivered, what we have to do with them, all the way up to the finished product, and even possibly to the point of who's going to receive it. One of the examples I could give is the Corvette factory, and the Corvette factory now. Every single Corvette that is being made is actually already sold, and so all the different features for that, whether it has a sunroof, whether it's got a V8 or a V6 or automatic transmission, standard transmission, or whatever, all the different little features and things, those are all pre-selected and defined so that, as the car goes down the line, each each feature or piece that needs added on, the color of it, all those different things are all in the computer. So when that car reaches that stage in the assembly, they know exactly, what's going on at that point, what color it's going to be, what kind of wheels they were selected or whatever. That's all selected in there. And then, the point when it's completed, they know, where it's going to be shipped to because they already know who's going to be receiving it. So, so that's this whole idea of computer integrated manufacturing. But here in the past, 10, 15 years, especially with things like smartphones and tablets and things like that, you've definitely heard of the IoT, or Internet of Things. Well, that applies also to manufacturing, and so they actually have a version of that they refer to as IIoT, or Industrial Internet of Things. And so the idea there is really just expanding this whole concept of computer integrated manufacturing, or CIM, to the point that not only do we know where all that's at, but we can look on, assuming you have access to that, obviously, but like the managers or whatever can look at their cell phone or tablet or whatever, and they can actually see where this car is in the line, and what's just been added, what's going to be added next, and just all that, where you can just kind of monitor and see what's happening and when it's going to be delivered and all that kind of information. All right, so looking at robots in manufacturing, okay, we run into some things there. Obviously, the robots are producing or performing automation, which is going to replace a more or less unskilled manual labor work. If we look way back when Ford first introduced the assembly line, it's like, okay, this guy sitting here, job is to do one thing, like to put the wheel on the axle or something, and that's his job, and that's all he does all day. And so he doesn't have to have a whole lot of skills. He just needs to be able to perform that one task. I mean, that was his given task. And so these types of jobs, obviously, robots can do. They don't need to take a break. They don't get tired. Things like that. They do, of course, still need maintenance and things like that, but they can, so some of this unskilled labor is being replaced. However, that just means that there's a larger need for technical skills for those to maintain those robots. Okay, so you kind of hear this a lot, well, do robots take away some jobs? Yes, they're going to take some jobs away, but they also create jobs. Okay, and so then, and again, there's a link here about a story. You can click on that. And they talk about all the different types of jobs that are going to be created. Okay. All right. So here's just some ideas of some different things. Electricians are going to have to install and maintain and troubleshoot. This typical industrial robot is actually driven by electric servo motors and things like that. So they obviously need that. The sensors and things are all need electricity. You're going to need technicians to program and calibrate the robots. You're going to need machinists to fabricate the robots and grippers and toolings. Obviously, engineers and project managers and things like that. So there's a lot of jobs that are created by automation. Okay, so just kind of as a comparison here, we look at the farm industry. In 1890 in the U.S., about 80% of the United States population was actually somehow employed in the farming industry. All right. But I don't know if you've looked much lately, but over the years, this automation and big equipment and stuff has also moved into the farms. And so as we look now at modern farms, the farm industry is actually only about 2% of the United States population. So it went down from 80% down to about 2% of the population doing farming. And yet we still actually are producing more food now than we were in 1890. All right, so some of the most common robot, and when I'm talking obviously industrial robots here, and industrial robotic manufacturers, number one is Fanuc, okay, and I just noticed here that Fanuc should be all capitalized because it's actually an acronym. ABB, Motoman, Seiko, Panasonic. So you see there's quite a few. These are the biggest players, but it's certainly not an exhaustive list here. Okay. All right, and so this is just a little chart showing you, and this was taken from this website listed here in 2019, but it's just kind of showing you that the Fanuc robot, the Fanuc is about 17% of the total installed industrial robots. And behind them is ABB at about 13 and Kuga at 13 and Yakasaka at 12. And then they kind of just grouped all the rest of them below that. So I was just kind of showing you that Fanuc definitely has the largest market share, but they're by no means the only player out there. All right, so in the United States, the largest manufacturer of industrial robots is a company called Adept. Okay, but most of those companies that we just looked at are actually from Japan. Okay, so it's slide wasn't advancing there. Okay, so all right, so there's two major reasons that robotics have come around. So when we look back in the early 70s, the cost of manual labor was much cheaper than it is today, but the cost of robots was much larger. And so, the cost of robots have recently dropped and been, continuously dropping over the past 30, 40, 50 years. And the obviously the cost of manual labor has been increasing. So with these two changes, obviously that's one economic reason why we're seeing so many more robots. Okay. Another issue is that industry demands like a 2 to 3 year payback for installing a new anything that industry is planning on installing. They want to try to recover their costs within 2 to 3 years. And so, with the robot is very, very expensive, it may be hard for them to do that, and therefore the management would be less willing to do so. But as the price of the robots drop, that helps. All right. But another big thing was the microprocessor. So in the late 70s, the development of the 8080 and 8088 processors and other similar processors. I mean, processors have been around for a while, but they really started improving at that point, which helped improve the reliability and accuracy of the robots. And so those, the economic reason and the microprocessor, the improvement of the microprocessors, both of those two factors were the key cause to the growth of industrial robots in the manufacturing. Okay. All right. So in the book, they kind of talk about hard automation and flexible automation. Okay, so automation is just obviously machinery that's been designed for completing a task. Okay, so when we look at, say, hard automation, it would be like an automatic bagging machine or something, and that's all this thing does. Okay, and so it's not actually, your book uses this term hard automation, which is a given fixed thing that they don't really consider robots as part of that. It's just equipment, PLCs and servo motors and lines, but everything just has like one task, and it does that one task. So if we go back and look at the original definition of the robot, you remember one of it was reprogrammable, was one of those key words in there. So when we talk about hard automation, we're talking about each step along the line. It's designed, it can only really do one thing. It was designed for that one thing. But if we get into flexible automation, then we're getting into the point where that's where robots, they can be reprogrammed to do various multiple tasks. Okay, and so they're not just designed to do one thing, like seal up a bag and something like that. Okay, so again, the slide's just kind of reiteration, the reprogrammability of the robot. Okay, and it can have multi-purpose. Okay. All right, so one of the things that we kind of goes along the line with that is in the manufacturing system, we can classify the different types of things that we're going to build or manufacture into about 5 categories here. The first one is considered the project. Second is job shop. Third is repetitive. Fourth is line, and the fifth is continuous. Okay, so when we look at project, in general, projects are not applicable to robotics because they're large, complex jobs, but you're only going to maybe build one of them. Okay, so an excellent example of that would be something like the Empire State Building or the Sears Building or the Eiffel Tower. These are large projects, obviously, but only one of them was ever built. I mean, other buildings were built and things, but each one of these had a unique aspect. Along with that goes bridges and roads. Okay, bridges, there's, thousands of bridges all over the place, but each bridge, even if it has essentially the same design as the bridge 2 miles down the road or whatever from it, it's at least somewhat unique because of the terrain that the bridge is designed to go across and stuff. So there's uniqueness to each one of these project things. And same way with roads. There's a lot of uniqueness to that. And so in general, then, robotics don't really apply to projects. Now, we are starting to see, though, that maybe the robot's not designed to just do this whole job, this project, but we are seeing like a lot of robotic welding in like bridge design and things. We're seeing that they're doing a lot of the welding or something at the manufacturing site using robots to do that, because robots do a very nice job of welding and generating a constant repeatable bead, which improves the strength of the joint, things like that. So we are seeing use of that in aspects of these project type jobs. Another one is the job shop. Job shop is not maybe one given project, but something that you're going to make 2, 3, 10, maybe even 100 of these, but it's relatively a small part that you're making, and maybe you're only going to do it once, or maybe you only do it once every couple of years or something like that. And so by the time you got around to reprogramming the robot and testing it and making sure it completes the job the way you wanted, it could have just been done. And so that's kind of the idea of this job shop classification. It's like, well, we're not just doing one as we would in a project, but we're doing just a few. And it really doesn't make sense to go out and spend thousands of dollars on a robot and programming the robot and stuff, and then have to, then that robot maybe won't be good for the next job that comes in, even though it's reprogrammable. Maybe it's too small or too big, and those kind of things. Okay. Now, repetitive jobs, on the other hand, obviously are definitely applicable to robotic work. Okay. So repetitive jobs have pretty high volume, and the parts are going to move through several different work cells or places within the line. And maybe you're building 2 or 3 different types of parts for that. So you see here like three different types of water pumps for different cars. So you got different size engines. So this line's maybe producing the water pump, but because of the different sized engine, you got 3 different size of pumps, and maybe they have some other slight differences in them. Okay, so that would be a repetitive type job. The next would be the line, which is also applicable to robots. This is, for an assembly line for manufacturing cars and trucks, where in general, you're making, Corvettes, as I mentioned earlier. So you're going to make, 100 Corvettes today, or however many it might be. And in general, they're all the same body, the same frame, maybe 2 or 3 different engines, but there's going to be some uniqueness to them. They're going to be different colors. They're going to have some different features on them, things like that. But so that would be like the assembly line. And then the final one here is continuous, which is what the book referred to as that hard automation, where it's like we're producing a lot of this, and we're producing it constantly, very, very high volume, but the equipment on the line is just doing one job. Okay, so an example given down here at the bottom is manufacturing of carpet, but it could just as easily be toilet paper or something like that, paper towels, something that you're going to make lots and lots and lots and lots of these, but you don't really need a robotic arm kind of thing to do anything there other than maybe palletize it at the end of the line, but the rest of it is just a continuous job or motion that needs to be made at that place in line.